Alrighty, folks, how are we doing today? We are starting a lecture that has grown and shrunk and grown again, and I don't know where it is now, but I've been given this lecture, a version of this lecture, for as long as I've been teaching, which, as we decided on the first day of classes, is a little bit longer than some of you are old. It started out as 15 billion years of history in 15 minutes, because that's about, I don't say all I knew at the time, but all I felt that I could or should convey in a 100 level course. And that was mostly about the creation of the earth. It was, I guess, sort of the beginning of my cosmology PowerPoint. It still exists, but I don't really straight up give anymore. And then over the years, it's grown to include, well, a wide-ranging number of topics. Okay, all about the Earth would be a great title for this. Everything you ever wanted to know about the Earth, we're afraid to ask, would be another one. But I decided on something vaguely academic and scientifical, and we went with investigating the Earth. Point being that this content comes from arguably a handful of chapters, if they were even all in your book. Okay? So, I don't want to say that you don't have a whole lot of backup on this chapter. Okay, the introduction, the prelude. Again, any one of these terms we talk about arguably should be found in the index and discussed on at least some page in your book, but there is no dedicated chapter that encompasses this conversation that we're going to be having. And again, I talked about this in the beginning of class this semester. For you book readers out there, I promise you we will be getting to. Today we're going to talk about minerals, and there's a chapter in your book actually called Minerals, kind of. We'll get there, all right, but we aren't there quite yet. So this stuff is in your book, and again, if you ever want some support materials, I recommend the index for one of the topics instead of going to the table of contents and looking for, a chapter called whatever. But, so yeah, so it's all in there. 85% of it's in your book. But it's spread out here and there and everywhere. So what have you been staring at here while I'm talking to you? The Earth? Okay. Cool. What's the... Huh? What's the blue stuff? Excellent. Okay. How about the white stuff? Clouds, and the clouds live where? Atmosphere, in the air. Good. How about the green and brown stuff? What do we call that? Land. Good. Earth. Yeah. Well, the whole thing is the Earth, and that is one of the things that's an interesting concept for a lot of folks, is that deep down underneath the ocean floor, is still the surface of the Earth. All right, even though it's a really big puddle. All right. But it is still the surface of the Earth, and you could arguably call the top of the ocean the surface of the Earth too. So it gets a little weird. But yeah, so everything we're looking at here, and believe it or not, those seem like silly questions, but that's some of the stuff we need to get out of the way, just to make sure we're all on the same page. We may give you slightly more complicated terms for that stuff, but yeah. Is this a real picture? Could it be? Yeah, totally. Unless you're one of those folks that aren't really sure if we landed on the moon yet, you could all probably agree that this is very good, likelihood that this is a real picture. But again, could you believe it or not that not that horribly long ago, we didn't have a picture like this? Okay, all things considered, not that long ago. Your great-grandparents, perhaps. Let's go back to that. They didn't maybe have a real picture to look at. So that's kind of wild too. All right? Time is weird. Time is weird. We I don't know, it hasn't come up in a while, but yeah, we kind of have these jumps in our collective memories. You go back in your mind, you go back to the to when your grandparents or whatever, your great-grandparents, maybe you guys get it every year, this gets older and older, but and then we go back to like old-timey stuff, maybe gangstery things in our mind, and then there might be like Revolutionary War, and then you've got cowboys and Indians in there somewhere, and then we kind of mentally all jump to like Egypt and the pyramids, and then we don't know where to go from there. We've got these weird little time stamps in our brain. But yeah, we don't need to go anywhere near that far back to not have a picture of the Earth, at any rate. So we decided what the Earth is, and the Earth is floating in what? Space. Good. All right, well, what's space? Well, we're going to talk about that. Space is a lot of stuff. This is not like in my Earth science class. We get a lot more into that, and that's part of what separates Earth science from geology. Geology is just one aspect of Earth science, and I use this lecture in, I use it in geology, I use it in Earth science, I use it in environmental science. So this is pertinent for all that. But we won't be talking in this class geology. We won't be talking too much more the rest of the semester about space. So if you really dig that stuff, sorry. So what is space? Well, space is a lot of stuff. I watched some interesting little, I don't even know what it would be, a video for lack of a better word, last night as I was bored and flipping through YouTube on the television, and talking about space-time and how it really is not just this empty void that we all picture. Well, it is an empty void, but it isn't an empty void, and that's where he started to, wax too philosophical for me. But, right now, for your mind, picture space whatever you've always pictured space. I grew up in the era of Star Wars. I was 8 when Star Wars came out. So I've grown up with the terminology, much like you guys have. I borrowed some of it. I'm not a complete Star Wars fanatic. Don't be, please don't throw me in that pile. Not that there's anything wrong with that, but I use terms like force fields, okay, which really, wasn't a common idea until then. I think I even mentioned tractor beams every so often when we talk about gravity. So we have a couple force fields around us, all right? We have one called the magnetosphere, and we have another called the Van Allen radiation belts, all right? And the magnetosphere is really cool. It is a product of, it is a function of the Earth. The magnetosphere is caused by rotation in the core. May or may not remember, there's 2 parts to the core. You've got a molten outer core and you've got a solid inner core. You'll see that all later. I'm just kind of introducing this here. And because the Earth is spinning, the metallic, the molten stuff is sloshing around the solid stuff, and it creates energy. It's polarized, positive, negative, just like a battery. You know those as the North Pole, the South Pole, okay? But that creates an energy field around us. And that energy field actually filters out some stuff. What stuff? The solar winds. What are the solar winds? Nasty radiation coming off the sun. We're not going to get more into it than that. Suffice it to say, it's a great thing that it's in place. Interesting little side note about the magnetosphere, or as I like to say, the magnetosphere, is that it, as far as we can tell, looking at the rock record, because it is magnetic, anytime that iron is molten, it aligns itself, polarizes itself not polarizes, it aligns itself with the poles. Well, looking at the rock record, we see that apparently every so often, north and south reverse. and which is cool. And as a student, I first said, well, we had plate tectonics going on. Maybe the continents, moved around this, that. Of course they did. And of course, iron was molten and solidifying and crystallizing while that was happening. So there is that aspect. But even that aside, that removed from the equation, they're quite convinced that there's these polar reversals every so often. And again, I'm fine with that. The only problem is as I just explained that to you, that the magnetosphere is a function of the molten sloshing around and presumably, you may have worked with motors when you were a little kid, little battery motors. When you switch the wires, it makes the motor go the other way, right? I think I remember that. So in my mind, how the hell else are you going to reverse the poles except to reverse the spin of the Earth? And that's, of course, not really an option. So I'm not sure they've figured that one out yet, but they are quite sure it has happened. Actually, if you look at a cross-section of the ocean floor, which we have done now that we've got submarines going down there with all kind of cool equipment and whatnot, there are bands or stripes. It's not visible, but there's bands or stripes of polar reversals spreading out from the center of the Atlantic and everywhere else, I'm sure. They match on both sides of the spreading center. It's a thing. So there are some things in science we don't know why they happen, but we're pretty dang sure they're happening. This is one of them right off the bat. I don't mean to throw uncertainty into the mix so soon, but get used to it. Kidding. All right, so magnetosphere, really important. Okay, really important. You may have been reading the North Pole is going crazy lately. Maybe we're coming up to a reversal. It always moves. That's why you have that setting on your little screw on your compass to change where magnetic north is. If you're using a really old map or a really new map, you need to set your compass to match the map. So we've known the North Pole moves for a very long time, but I guess it's moving crazier than it usually does. So we'll see. Earth time and our time are two completely different scales. So could be sometime soon. Maybe, your grandkids will see the reversal. Who knows? All right, then we got these Van Allen radiation belts, named after, I'm sure, scientist Van Allen. This is the stuff we actually have to worry about when we go into space. It's good and it's bad. All right. It does, again, parts of the magnetosphere do grab all this radiation. But when we go out in space, as you may have heard, again, depends how much you pay attention to this stuff. One of the things you have to worry about is radiation. So when we go through these belts, it's concentrated. Okay. Again, it serves as another filter for us, and it traps stuff. That's why it's formed over there. It wasn't always there, kind of thing. It's built up over the years. But it's also, provides a bit of an obstacle for us, something we've got to get through. It's like the first boss battle, maybe. Well, gravity's the first boss battle, but it's out there and it's an issue for space travel. So here's a little, just some textual version. And this is up on your class site. Again, you shouldn't have to be frantically copying all this down. Protective shield created by the core of the Earth. The liquid outer rotates around the solid inner, creates this polarized energy field. That's a really cool image, I think. This was probably somebody's master's thesis or something. That giant space spider, or space squid. Let's see, 1, 2, 3, 4, 5. Yeah, I think it's got more legs than a squid. It's a cosmic spider. Doesn't have rules. There you go. No rules. It looks like, it has the head and the legs and the tentacles and even a thorax there, or an abdomen. But if you look at it close enough, it's pinched together in the middle there. Those are our north and our south poles. All right? So the Earth is almost, if you don't already know this, you will, almost straight up and down. It's tilted on its axis. So those pinches there in the middle represent the two poles. Why do you think it's kind of flailing off into the upper right-hand corner of the slide there? What's going on? Yeah, the sun's being pushed away by the sun, exactly. That's that solar winds and whatnot. It's dragging it off, okay? Yeah, it's smushing it in the front there. I'm not sure what they're trying to show with that sort of little bubbly thing around all of it, but yeah. Maybe. A little bit more about the Van Allen, but I guess I have to zoom out. I was going to let it be, but we're losing text now. Folks at home, there's just stuff that's off the screen. You wonder what I'm talking about. There we go. So we didn't know about this stuff till 1958. We had a satellite up there, an area within the magnetosphere. The radiation of solar winds are actually trapped. There's 2 belts, sometimes more. So it grows, it goes away, waxes and wanes. And as I said, this is something we need to worry about when we're traveling outward. Now, I'm not getting down and dirty into, well, at this many miles you've got this many miles you've got. If you want to learn more about this stuff, any one of these topics, you guys know more than anyone. A little bit of Googling, you'll be there. And in science, just as an FYI, Wikipedia is not a bad place. I know you come up through school with, and maybe it's changed, but you guys keep hearing it's unreliable because anybody could change it and so on. I've found over the years that they don't really screw around with the science stuff that much. I'm sure there's trolls out there on a handful of sites, but
most official officiated concepts aren't allowed to be edited by.
Well, there you go then. Okay, I didn't know that.
They cracked down on that back in like the mid-2010s.
Okay, so it's not as easily editable as it used to be. That's good. But point being, instead of going to some random site about, or on Reddit or whatever, about Van Allen belts, go to its Wikipedia page or any of these things, and it should give you a fairly good idea about it. And what I love the most about it is that any word that you don't know or you want to learn more about usually is blue, and you can click on it and go to another article. All right, and that's how you get lost for 3 hours sometimes. But nonetheless, that's a good loss. So I don't go, and remember, I don't test you any deeper than we talk about in lecture. Okay, so don't expect me to ask you, well, where are the Van Allen belts in miles? No, you want to know? Look it up. Or you could always ask me and I'll look it up for you, but just more Van Allen stuff. Because this has it looking like it's really far away. So, you'd think I would know too, but I don't. All right, let's get a little closer to Earth for a little bit here. So we're going to go back down to where that white stuff, those clouds you guys all correctly identified, and good for you, by the way. All right, so our atmosphere, our air, gaseous bubble, you've also maybe heard of it called an envelope, but it's got a lot of, metaphors, analogies that people use. What is the gas we really, really need in order to survive? Oxygen, yeah. A lot of folks surprised to find out that oxygen is not number one, and really nowhere even near number one. Well, it does have some other issues. Maybe it would stabilize, if we mix it with the right stuff. But yeah, it's pretty low there. But it is exactly, what we need. Oxygen is one of those weird ones. Huh?
Should be a lot higher.
Well,
probably a lot lower.
Yeah, definitely.
Like
We're gonna start with it being a lot lower here eventually. But you guys personally, you lose a little bit of oxygen, you get a little too much oxygen, you notice it either direction really, really quickly. But so you guys are primarily nitrogen breathers, and when I first started putting this together, I talked to some of my biology friends, and I'm like, okay, so nitrogen, what's up? And we went back and forth, and really it sort of just passes through us. It has a couple functions. If you know anything about diving, you know that there is a link between diving and nitrogen. It's called the bends. Okay, so it's not exactly inert, but for the most part, it just We just deal with it. But that is the majority. Over 3/4 of the atmosphere is nitrogen, and you got just under 1/4 for oxygen there. I'm a geologist. We love the round. You guys will find that out. Okay. So that almost equals 100%, right? So all that other stuff that's out there is in a really teeny tiny little percentage. The atmosphere is here because we have gravity. All right. We'll talk about gravity a handful of times in this conversation. But first and foremost, we know it and love it because it has held those tiny little gaseous particles very close to the Earth. All right. One thing you will be made aware of is something called the ozone layer. Not because of probably why you typically hear about the ozone layer, but a different reason. And the ozone is in a layer we call the stratosphere. You may have heard of the stratosphere. The stratosphere is the layer just above where we live, which is the troposphere. Okay? So you live in the troposphere. It's the first layer of the atmosphere. Second layer of the atmosphere is called the stratosphere. You will see a diagram eventually. In the stratosphere, we have something called the ozone layer. Well, you guys tell me. Maybe you do know. Why is the ozone layer important? Reflects what? Something with the sun? Yep. Yeah, well, one of the radiations coming out of the sun. Anybody know which one? Photons would be light, right?
Yeah. Light is pretty dangerous. So
it's not the one we're concerned about right now, though. Ultraviolet, yeah, UV rays. All right, UV rays. So, ozone is very important. And as I said, you'll hear about it with some frequency. Okay. A little bit of, I don't know, call it physics if you want. A little bit of physics for a couple minutes. Not too horribly scary stuff. D equals M over V. B equals F over A. F equals MA. F equals MA is really, I don't want to say kind of important, but that comes up probably more than any of these for you guys. Force equals mass times acceleration. That's why when you're playing football and some really, really big dudes coming at you, you go flying in the opposite direction. All right, so what's going on here? Density equals mass, for those of you that don't remember. All right, D equals M over V is density equals mass over volume, or mass per volume. You could always read that slashy sign as per or divided by. Pressure is force per area, force over area, which is why I had to throw the force equation in there. So pressure is mass times acceleration over area. Now, I am not going to have you guys calculate these things, but you kind of need to understand them a little bit in order to understand air pressure, believe it or not. Why do you need to understand air pressure? Well, you really don't, but the weatherman tells you about it anytime it's on. So you may as well know what it is, right? You hear about air pressure all the time, and it has to do with why these different fronts, okay, these weather fronts move around. Weather, by the way, meteorologists, freaking incredible the amount of math that is involved. That's why we love computers, okay? Fluid dynamics, like Calc 4 kind of stuff. So there's a huge difference between a weather bunny and a weather person, and there are male bunnies. I'm not just talking about the ladies there. There's both. There's pretty little people on the Weather Channel just smile and give you the weather. There's a difference. Not all meteorologists are attractive. That's the problem. It's a joke. All right. Anyhow, so here's the rule: both air pressure and air density decrease as you leave the surface. Why? Well, gravity. What do we know about gravity? Somebody tell us something that we know about gravity other than stuff falls because of it. True. Force is applied to the ground. All right. True. That's true too. Neither of which what I'm fishing for, though. What is it caused by? What's it a function of? We're totally not getting into relativity and all that stuff. Just Newtonian physics. Yeah, gravity is a function of mass. So the more mass you have, the more gravitational pull you have, but also the more you're affected by gravity pull, somebody else's gravitational pull. All right, so it's a double-edged sword. So gravity is a function of mass. Okay. As such, I won't fish for this one. We'll just cut to the chase. The closer you are to an object, the more you're affected by it, or it affects you, kind of thing. So gravity is also a function of distance, for lack of a better word. So what's happening here is that this atmosphere, all these molecules we're talking about, they're attracted to the Earth because of gravity. And the farther you go out, well, the less air molecules there are. And again, you knew this. It's, you go up way high in an airplane and there's no air up there, okay? Or at least less air. It's less dense, to use the right term for a moment here. You knew this already. You just might not have stuck it all together as to a why. So if you think of this as a color fading thing, all right, that color is going to be really, really dark near the surface of the Earth because there's so much density packed in there of all those air molecules, and then it lightens up as you go outward from the surface of the Earth. That is because of gravity. So the mass per volume of air, any given volume. Air is tough because you can't see it, right? So in my mind, or when I used to do this stuff on chalkboards, I'd always just draw this happy little cloud kind of thing, okay? That's our air pocket. So how many air molecules do you have in that little cloud thing versus, that gives you your density. Sometimes it can be tightly packed, sometimes it can be emptier. If I still don't have you on board here mentally, think about a bonfire. Everybody's been to a bonfire, stood in front of a fireplace. The closer you are to it, the hotter it is, right? As you back away, it gets cooler. It's exactly what's going on with the density of the atmosphere. The closer to the Earth you are, the thicker it is. The farther out you go, the thinner it is. All right? So that is air density. Now, why did I start with that one? As you see, the density is a function of the air pressure. All right, even though it doesn't show up in the equation directly there. And you see the M, the mass, there it is. But it's kind of hidden. But the air density, air pressure is a function of the density, because the pressure, if I could use the term incorrectly for a moment, is nothing more than the weight of the air pushing down on you. That's what air pressure is. Again, weight. What's the problem between, you guys had this in your lab book, first question, well, not first question, first lab. What's the difference between weight and mass? All right, somebody tell us what mass is then. Add to her thing. So weight is gravity's pull on your mass. What's mass? Sum of your matter. All right, sum of your matter. So, yeah, let's see, a wop an arm or something like that. Yeah. So then and it doesn't have any difference. Does it have any bearing on your lives? No, not at all, because more than likely you're not going anywhere where the gravity is different. We could use them interchangeably, okay? And it's the same thing. They love, the physicists are a pain in the butt sometimes. They love to nitpick about velocity and speed, right? What's the difference between velocity and speed? Off topic, but nonetheless. Yeah, well, they don't know what a vector is. What's a vector? No, some of you do. Yeah, it's speed with intent, right? It's a direction. So when you use the word velocity, it's supposed to have a direction in it, for the vector. Okay. I don't know why they never spoke clearer myself. I believe in physics. I trust physics. I don't get physics, and I think it's because of their vocabulary words. At any rate, so back to the point. We should have said it's the mass of all the air pushing down on you, but you guys all know what I mean when I say it's the weight of the air. Okay? Technically, yes, they're different. So, one of the ways that you can think about this is, you remember that they used to only sell it at Spencer's, now it's everywhere. That little rectangle with, like 300 pins in it, and you use it to make impressions. Usually there's a middle finger stuck in it because, teenagers. But the thing with the pins. All right. So imagine if that was hanging down sort of vertically, and you were walking through it, and those pins would go up and down as you walk through it. All right. The different height of those pins sort of represents the air column above you. So sometimes there's less air above you. Sometimes there's more air above you. You're at the top of the mountain. You've got less air above you. You're at the bottom of a deep, deep valley. You've got more air above you. All right, you follow? So your air pressure is going to increase or decrease accordingly. Now, there are air molecules. It's not a whole lot. One of these days, I'm going to take some time out of life and study barometers. They've always intrigued the heck out of me. I love barometers. Barometer is what they use to measure air pressure. All right. And the weather person will say, 29.97 inches of mercury. So at some point, somebody put mercury into a U-shaped tube and a little ruler taped it onto one side of it and said that, hey, this is the standard air pressure. I'm sure there were a lot of other things. We don't use mercury anymore for a handful of reasons. But that's what it is. It's literally air pushing up in this tube mercury to a certain level. All right. And that's for some reason I was probably one of 6 people on the planet that was excited when iPhones got barometers. They're electronic. There's not well, I'm sure there's mercury in there somewhere. But it's not that old-fashioned thing, but there's other ways to measure it. Back in, you guys probably never used a handheld GPS unit, but some of you might have played with your parents. That was a vital thing for them as well, because that helps you with elevation. Okay, so lots of neat stuff. So again, I started with those equations, but please, I'm never gonna put them on a test for you. I just kind of wanted you to see how they're related and all that stuff. And one of our physicists just walked by. Hopefully she didn't hear me making fun of physicists. But all right, anywho. So air pressure and air density, I think we have a handy-dandy little graph. Everything's better with a chart, right? So at the moment, I can't remember what that red line is for. It's one of those things. It's actually the measuring the millibars there, the pressure down on the bottom. What I find interesting about this diagram is that diagram, the picture of Mount Everest there. Now, everyone is so familiar with Mount Everest. We all know how high it is, right? No, but it's really high. We know that. And we've heard that some people have actually climbed to the top. That's about all we know, right? So what we can show here is that they were above more than 50% of all the molecules of air that were out there. That's why, those Sherpas are really special people. They're acclimate, and so on and so forth, and why you need oxygen, most people. Again, if you're smart, you practice a lot, you get used to living in, working in and exercising in on top of it all, not just sitting there watching YouTube, in lower oxygen. Now, you don't have to go to the top of Mount Everest to experience this if you've ever been, let's say, out to Colorado or something like that. The air is legit thinner, okay? You can feel it a little bit. It again depends on your physical health and all that. Back when I first went out that way, I was smoking a pack of Marlboro Reds a day. Don't smoke, smoking's bad. But I was in better physical condition than I am now, mind you. But nonetheless, I felt it more than some other people did. It was the 90s, everybody smoked. But at any rate, smoking's bad. Okay, so what do we got here? So we got up there where airplanes were. I was just in an airplane last week, and I really don't like hearing how many thousands of feet up in the air we are. But yeah, they're up there, and unfortunately, this is in kilometers. And there's probably 1 or 2 of you that can process that in your heads right now. I apologize, it's not in good old-fashioned American. But all right, so what do we got here is our bullets. Atmospheric pressure is a function of density. Air density decreases with altitude because why? Gravity, good. All right. And atmospheric pressure then also decreases with altitude. So because density decreases, pressure decreases. Can we move on? We good? Okay? Okay? All right. Well, I was close. 29.92. I forget what I said. 9.7 maybe. All right, so air pressure. Air pressure we think of as a 1-inch square column of air and as high as the atmosphere. Back to the pins in that weird little pin thing. So 1-inch square and as high as the atmosphere, it weighs 14.7 pounds. Right now, you guys are under 14.7 pounds of pressure per square inch. Why don't you notice that? Well, because you've been under that for 20 some odd years. Why don't you notice it when you pick something up? Because that's also under the same exact pressure. So everything is sort of normalized, equalized, whatever word you want to use. Everything you're touching is under the same amount of pressure. So it's essentially zero. It's equal. And I told you we measure that in mercury. That 1 ATM, that's an atmosphere. So 1 atmosphere, as we call it, is 29.92 inches of mercury. Hg is mercury. And I do believe that's at sea level, which we are not. We're not that much higher than sea level. What's our elevation? Yeah, you're not helpful. According to my watch, we're at approximately 616 feet. I wanted to see if Siri agreed with my watch. I guess you could Google this. What is the elevation of Utica, New York? Just give me a straight answer. This is why I'm not worried about AI taking over the world. So we're right around 600 feet, I believe.
456 feet.
Thank you. 456 for those of you at home. It did seem high, but I wasn't going to argue with my watch. It might shock me or something.
I got a different answer. No, 813.
Huh?
813.
813. There's actually we call them benchmarks. There's actually a benchmark by the Geological Survey nailed into the ground down at the train station. But yeah, I think the watch is usually fairly accurate. I tested that out in Arizona this summer. But again, it does a lot of variables. You get the moisture, too dry, too wet, changes air pressure.
USGS 386.
386. All right. So here's the other thing, though. It changes hugely. I may or may not have mentioned to you guys at the beginning of the semester, we recently moved. When I talk about my family history, my son went to Proctor, my daughter's going to New Hartford. We moved into New Hartford. Our elevation actually went up 250 feet. So coming from downtown to up here, going to New Hartford, a couple hundred feet. When we're nitpicking about this stuff, it adds up really quick. So and we're on the second floor, which added 20 more feet to my number, if it's accurate. So at any rate, and again, that's why geologists are around. One of the many reasons why. All right, so air pressure. Unlike air pressure and air density, temperature vacillates wildly. That red line in the center there, that represents temperature change. A move to the left is a decrease. A move to the right is an increase. And of course, not moving means it's staying put. So what we see what can we tell about temperature in the troposphere? Which layer is the troposphere? You guys remember? The one that we live in. So the very bottom one there. So it's a move to the left. So what happens as you go up in the atmosphere? It goes down. Good. All right, it gets colder, yeah. Then it levels out for a while. Then it increases as you go through the stratosphere. Then we hit the mesosphere, and it goes down again, even a little colder than it was. Then we go to the thermosphere, and it ends. There's actually another level up there called the exosphere. You'll see another slide in a minute. It keeps getting hotter and hotter and hotter, actually, which is something we'll talk about. But let's go back down to Earth. And go there. This is something, again, we already knew, right? When I was growing up, bomber jackets were a huge thing. Now, being way older than I was back then, I realized that 40 years is not that huge of a difference. Back then, everyone was wearing these, again, a bomber jacket, but like the World War II fighter pilot ones. The only thing that seems to have stayed around fashionably are those silly hats, which are back. And we just thought it was cool, they got cool leather jackets and so on and so forth. But why'd they wear all that stuff? It was cold up there, okay? Again, you're going back to 1940s, 1930s technology in those airplanes. They were cold. You never see any fighter pilot gloves, though. I don't know why they didn't have gloves. You think they had gloves. They probably all just fell apart. But everyone loved the jackets at any rate. And the floppy ear hats. So yeah, we already know it's cold up there. And every so often you find some poor soul that tries to stow away in an airplane. There's air issues as well, but oftentimes they're frozen. Yeah. So, anywho, so it goes down in the troposphere, it levels out, goes back up in the stratosphere, back down, Oh, and again, don't worry about those pauses, those dashed lines in the middle, all right? That's just more vocabulary for no good reason. Of course, there's a boundary of some sort between the mesosphere and the thermosphere. We don't need to name it, at least not in here. And definitely don't worry about the homosphere and the heterosphere. Don't need those words. This quite nicely has Fahrenheit and Celsius on it for you. You see that the average ambient surface temperature is right around 60 degrees. Not a fact you need to remember, but interesting to find out. And by the time you get up to the top of the troposphere, we are just about at negative 60. I can't tell from my angle if that goes all the way to 80 or not, but I'm going to stop it halfway in between negative 40 and negative 80 Fahrenheit, and we'll call it a negative 60 up there. So it drops pretty rapidly in a little less than, a little more than 5 miles. Many of you drove 5 miles to get here today, if not more. That is something else that I like to talk about, possibly a little too much, is how quickly things change vertically on the Earth, whether you're going up or down. We have a lot of freedom horizontally. Okay, as long as you've got a car and gas money, you can go as many miles as you want to.
I get a crazy change sometimes because during the winter, if I'm down in town, it might be clear roads and everything, but I just have to turn up my hill. The hill rises about 550 feet, and I'll drive right into a blizzard out of nowhere.
Yeah, that is very true. The weather can change drastically around here, going up one side of the valley or the other, for sure. But that aside, you're still going up there without any breathing equipment or mining equipment. That's kind of where I was going with that. You're very true though. But we're very limited to the surface of the Earth, and even once we did create these crazy machines that allow us to fly, okay, or if you've ever watched on Discovery Channel or whatever, these folks that are going down deep into the Earth, they're coming out, practically just in loincloths. It's so dang hot down there, all right, and a lot of pressure and so on and so forth. Things change very quickly and vertically. All right, before I go off on my other rant, let me check the next slide. Yeah, we don't need to do that. Well, we can leave it on here. So we have a vocabulary word for you here, lapse rate. And lapse rate is the average temperature decrease with altitude increase. In other words, as you're going up, the temperature, we've just been talking about this, they can measure it. And it's about 3.5 degrees Fahrenheit for every 1,000 feet. All right. This is for the troposphere. It's not that entire chart as you saw. It doesn't always change, but for the troposphere. So I'm sure if you did the math, you would come up with what you're seeing on here. Don't need to do the math in my mind, but we're going to trust our diagram. So going back to our diagram just for a moment, I wanted to talk about the fact that as we leave the thermosphere, thermo heat, right, therms, that line goes up and it kind of truncates there on us. If this had the exosphere on it as well, that temperature line would just keep going up, 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 up. So that tells us that space is really, really hot. Is that what Hollywood's taught us, though? No, not at all. Now, we're used to Hollywood lying to us. In this case, they're actually not, though. So how could they both be true? So what is temperature actually? Anybody remember? Huh? I didn't hear you. I apologize. Movement of particles. Yeah, so what about the movement of particles? Somebody help her out there. How fast they're moving. Okay, and what's hotter, what's colder? Yeah, fast is hot, cold is slow. I don't know if I was doodling when my teacher was talking about absolute zero, but absolute zero never made any sense to me as a student. I kind of thought it's so cold that even molecules can't move. I missed like the entire point there, right? Well, no, it's molecules aren't moving, so it's that cold. Not that that's much better, but it's a different approach to the same idea. So if temperature is molecular speed, all right, and the faster something's moving, we call it hotter. The slower it is, it's colder. That's fine. We've got that. What it boils down to is that temperature is a sensation, right? You have to feel it. Well, what did we just spend, Lord knows how many minutes talking about out in space? Is there a whole lot of air molecules out there, or are there not a whole lot of air molecules out there? There's not. So if temperature is a sensation, and you need to feel those air molecules in order to feel that sensation, that's how they can both be right. If you come across one of those air molecules, that sucker's hot. But you're in that void, as they always call it, that vacuum of space, the cold, hard vacuum of space, blah, 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 all that stuff that you hear. If you're not in contact with any of those air molecules, essentially you're feeling that absolute zero. So, in that sense, they're both right. Yeah, it's kind of neat. Now, one more tangentially related thing while we're here, because we don't get a chance to talk about it anywhere else. You guys have been holding your pens or your pencils or whatever for a long time now here. You can, what I want you to do is set down whatever you've been touching, and I want you to feel your desktop. And you folks at home, feel your tabletop, or whatever you want to do. All right? Does it feel cold or whatever? Cold, yeah, a little bit. All right, now find a piece of metal on your desk. Colder. Okay, you all agree? Feels colder? Okay, good. Is there any reason you could come up with, logical or otherwise, why that metal is colder than the top of your desk? Shh, don't tell me the answer. No? Nobody knows? All right. Yeah, so what is that? For those of you that at home, someone said that it conducts heat better. What does that have to do with anything? Is it actually colder in that because it conducts heat better? Why? Why does it feel cold? Why do you feel it as colder? Well, yeah, exactly. It totally has something to do with it being metal. And because metal's a good conductor. Oh, we don't need to involve electrons. All right. So, it's not cold. You are. It's stealing your heat because it's such a good conductor. It's stealing the heat out of your finger better than the surface of your desk is, than the wood is, or whatever this is. Vinyl of some sort. All right, so because it's a better conductor, it's stealing your heat better. It's not cold, your finger's cold. And that's true anywhere. Okay, it's you. Remember, temperature is a sensation. So it's conducting that, it's sucking that heat away from you better than any other surface in this room does. So your finger feels colder touching that. Yeah. All right, anywho. Didn't blow your minds exactly, but something to ponder. There you go. Fun at parties. Fool your friends. All right. We're coming to a natural pause here pretty soon. I've been talking a long time. Hopefully you guys have been enjoying some of it at any rate. Here's our layers. And again, I'm not going to have you regurgitate these numbers. We're going to talk about a couple of them. We'll talk about the first one and the last one. Okay? Because again, what we have is usable air. In environmental science, I would talk about this because when we talk about air pollution, we've only got so much air and it's so close to the surface and, we're pumping out all this. It's like sitting next to somebody who's just, smoking that whole pack of Marlboro Reds right next to you and so on and so forth. Or behind a giant truck at a red light on a hot day with your windows down. Okay, we've only got so much air and we're constantly pumping this stuff out into it. And some of my other classes, I might talk about it in all of our weather, okay, happens in this 7 miles. And again, many of you drove farther than that today. It's not that high up. Speaking of not that high up, let's jump to the last one. Where's space? Space is pretty dang close, okay? This exosphere that we talk about kicks in at about 300 miles from here. Now, you didn't drive 300 miles today, but maybe, semi-recently you did. Over the summer you took a trip or something like that. Again, we could jet about the surface of the earth 60, 70 miles per hour pretty much as we want to. But try going that far up and things change really, really quickly. And how far does it go? Well, that's a conversation for a different class. All right, so what's up there? Well, we started giving you a couple of these numbers earlier. We gave you the top two, and the top two are all I'm going to hold you responsible for. All right, so the air is primarily nitrogen, it's about 78%, and oxygen, a big gap there in like percentages, right? But the two topmost, nonetheless. And then what else is in there? Well, you got 0 to 3% of water vapor. Now, I know in some of those August days and sometimes even September around here, it feels like a whole lot more than 3% of the air is made up of water, doesn't it? Again, just takes a little bit to notice a change. These things are fixed by Mother Nature at a level. And because of those levels, we get exactly what we see out here. This is something that always just astonishes me, how little people, and I'm not talking about you guys, I'm talking about the people in charge of all the crap out there, okay, the politicians and whatnot, how little they pretend to process this. Okay, everything we see now, whether we talk about the coldest weather in Vermont or the hottest weather in Arizona and everything in between, is because all of this is set at these levels. When you change these levels, things will change. All right, it's only 100%, even though this adds up to more than 100%. Don't do the math. All right, but you mess with the levels, things will change. All right, it has to. Argon. Don't know what the heck's argon's doing in there, but there's 1% of argon. I've been pondering that one for a long time, and then suddenly I was talking to a window salesman for some reason, and he was bragging about the presence of argon in between the glass panes. I said, finally, someone who knows what argon does for us. He had no clue. Just knew that it was there, and it was very helpful in the windows. Thank you, sir. Carbon dioxide. Here's another one. Oh, my God. Al Gore, Bill Nye, all these people have been going on and on and on about the carbon dioxide. It's 0.035. Really, get over it. No, it doesn't matter that it's a tiny number. Okay? What matters is that's what it's set at. And again, if it changes up or down, things change. And we know this because we have really, really, really old bubbles of air trapped in ice. And we can look at these percentages. And we know that as CO2 goes down, we go into ice ages. And as CO2 goes up, all that ice melts. And with that, because we believe in the hydrologic cycle, aka the water cycle, they taught you the water cycle when you were watching Blue's Clues, for crying out loud. The water cycle is real, right? There's only so much water on the planet. So when you freeze it, it has to come out of the oceans, and the oceans are lower. When you melt it, it goes back in the oceans, and the oceans get higher. Now, again, these people aren't idiots, right? They're far from idiots. They act like idiots sometimes. They understand this. They are being, I don't want to say paid not to understand it. They have to understand this. It's common, simplistic knowledge. Talking about the Discovery Channel again. And they're exploring some ancient Greek civilization that's now 50 feet underwater. Did you really think they built that underwater? No. It was land when they built that. Dry land. All right? And so on and so forth. There's so many things. And this is, and people get tied up and bickering back and forth about the ignorance of this and that. They have to understand. They just choose to ignore it. Sorry, tangent. Other gases. Again, a small percentage. But think about all the other stuff, including pollutants. I'm not, pushing off the importance of not polluting. But all of those things, again, a very small fraction of what's out there. But because of that, things are what they are. The current conditions are a function of the current composition of the atmosphere. When that changes, we should expect changes. All right? And as I said, that leads us to another section where we're going to stop here. We'll pick up here next time we talk.